Hello, I'm Sonali Gera, and I'm a graduate student in the Department of Physics and Astronomy. And today I'm going to be talking to you about building a quantum computer one particle at a time. I love going on a vacation, and every time I plan for one, I look at the world map and I think to myself, wouldn't it be great if I could go to multiple places at the same time? For instance, take a flight to Spain and a flight to Japan on the same day at the same time. That way, I don't have to choose between different places and I could do everything I want to do. If I had that superpower, I could even use it to solve problems faster. For instance, if I had to take a test with 10 problems on it, I could sit at 10 different desks, simultaneously solve a different problem at each desk, finishing the test 10 times faster than someone who doesn't have that superpower. While human beings cannot do that, individual particles like a single atom or a single photon has this special ability. If we could exploit it and make a single particle solve multiple problems at the same time, it would be faster than present technology. This is the idea behind a quantum computer. While we are decades away from having a fully functional quantum computer, research has shown that if we could build one, it would solve some problems infinitely faster than even the most powerful present-day computers. In nature, however, only isolated individual particles have strong quantum behavior. A collection of many particles loses all its quantum effects. And that is why human beings are not quantum, because we are composed of millions of atoms. To build a quantum computer, we have to work with isolated particles, like a single atom or a single photon. My job in the lab is to isolate single photons. Photons are particles that make up light. To isolate them, I use light from a laser, which is composed of millions of photons and collectively has no quantum behavior. I make this laser light pass through a tiny crystal that converts every photon in the laser light into pairs of photons. By detecting one photon from the pair, I can isolate the other one and use it for my experiments. Now, the tricky part is that not all photon pairs created by the crystal are suitable for our experiments. To solve that problem, I take the crystal and I put it inside a cavity, as I've shown in the slide. A cavity is a combination of mirrors placed such that the photons bounce back and forth between the mirrors and they get trapped inside the cavity. The cavity acts as a filter and allows only specific kinds of photons to exit. By tweaking some parameters of the cavity, like the distance between the mirrors or their angles, I can choose what kinds of photons come out. Once I have the suitable photons that I need, I employ them in my experiments that attempt to solve simple problems and would one day become a part of a future quantum computer. Thank you.